Imagine the ground beneath your feet starts shaking violently, an earthquake. Your first thought is to find cover, to brace for what comes next. But what if that was just the beginning? What if the shaking ground wasn't the disaster, but the fuse lighting a much bigger one? What if the rumble of an earthquake could wake up a sleeping giant? For a long time, the connection was written off as a chilling coincidence. But now, scientists have uncovered the secret trigger that links these two terrifying forces of nature. An invisible thread that can turn a tremor in the earth into a world-changing volcanic blast. And figuring it out is a very big deal for the millions of people living in the shadow of a volcano. The secret trigger that makes volcanoes explode. At first glance, earthquakes and volcanoes seem like totally different problems. Earthquakes are all about friction. The Earth's crust isn't one solid shell. It's broken into massive tectonic plates that are constantly grinding past each other. They move at about the same speed your fingernails grow, but on a planetary scale. When these plates get snagged on a fault line, stress builds up for decades, sometimes centuries. And when that stress finally wins, the rock snaps, releasing a crazy amount of energy as seismic waves. That's the earthquake. A sudden, violent release of tension. Volcanoes, on the other hand, are a pressure problem. Deep in the Earth's mantle, there's a world of molten rock called magma. Because it's hotter and less dense than the solid rock around it, it slowly rises. Now, this magma doesn't just hang out in huge open caverns of lava like you see in the movies. Instead, it often collects in complex, semi-solid networks miles beneath a volcano. Think less of a giant tank and more of a crystal-rich, slushy body. But this magma mush isn't just hot rock. It's supercharged with dissolved gases like water vapor and carbon dioxide. For a volcano to pop, it needs to be poised to erupt, with its chamber full of this mush and enough pressure straining to break free. For thousands of years, a volcano can sit quiet, a silent mountain holding back unimaginable power, just waiting for that final push. For centuries, history was filled with terrifying coincidences that just didn't quite add up. Take Japan, the year 1707. On October 28th, the Great Hoei earthquake struck. With an estimated magnitude of 8.7, it was one of the most powerful quakes in Japan's history, causing massive destruction and a devastating tsunami. The country was in shock, but the planet wasn't done yet. Just 49 days later, Mount Fuji, Japan's iconic sacred peak that had been silent for almost 300 years, roared to life. It was a cataclysmic eruption that lasted for weeks, burying the region and even the distant city of Edo, modern-day Tokyo, in a thick blanket of ash. For generations, this was just seen as a terrible chapter in history. Two separate disasters. A case of impossibly bad luck. But a few scientists and observers started to wonder, could the quake have somehow provoked the volcano? The question hung in the air for centuries, a geological cold case. Then, in 1960, another piece of the puzzle fell into place. The largest earthquake ever recorded, a mind-bending magnitude 9.5, hit Valdivia, Chile. The devastation was nearly total. And just 38 hours later, 200 kilometers away, the Puyehue Cordon Caule volcano erupted after being quiet for 4 decades. Coincidence? Or was this a pattern? The evidence was piling up that something connected these events, but nobody knew how. How could a crack in the Earth's crust in one spot cause a mountain miles away to blow its top? It turns out the solution to the mystery wasn't one secret, but a few. Scientists found that an earthquake's energy radiates outwards, creating 2 different kinds of stress that can mess with a primed magma chamber: dynamic strain and static strain. The most dramatic is dynamic strain. This is the shaken soda bottle effect. When a huge earthquake hits, it sends seismic waves vibrating through the planet. Picture these powerful ripples passing through a magma chamber. That chamber is basically a giant underground bottle of soda that's been sitting still for centuries. The magma is full of dissolved gases, all held in check by the immense pressure of the rock above. Then the seismic waves hit, violently shaking the chamber. Just like shaking a soda bottle makes the CO2 suddenly form bubbles, the seismic energy causes the dissolved gases in the magma to flash into bubbles, a process called exsolution. This sudden foam of gas and magma is way less dense and more buoyant than the liquid mush around it. It surges upwards, dramatically increasing pressure on the cap of the volcano. If that pressure gets too high, the cap fails, and you get an explosive eruption. This explains how even very distant but very powerful earthquakes can trigger a volcano. The waves can travel hundreds of kilometers and still have enough energy to give the magma that violent shakeup. But there's also a quieter trigger: static strain. This is a permanent change to the ground itself, and it happens closer to the quake. After a major earthquake, the crust doesn't just snap back into place. It's permanently warped. Some areas get squeezed, but other areas get stretched apart. Now, imagine a magma chamber is sitting in a part of the crust that gets stretched. The intense pressure holding that magma down is suddenly reduced. It's like slightly unscrewing the lid on that soda bottle. This drop in pressure also lets those dissolved gases form bubbles. This process, called vesiculation, makes the magma less dense and more buoyant, driving it upwards and potentially kicking off an eruption. And finally, you have the plumbing. Volcanoes are riddled with complex networks of superheated water and steam, known as hydrothermal systems. An earthquake can shake this plumbing apart, cracking the rock and opening new pathways for fluids to move. This can cause a rapid depressurization of the hydrothermal system, which then works its way down and disturbs the much larger magma chamber below, acting as the first little nudge that starts a catastrophic chain reaction. This intricate dance of waves and pressures is what scientists are now racing to map all over the world. It's a fascinating peek into how our planet really works. And if you think these deep Earth mysteries are as cool as we do, go ahead and hit that subscribe button to join us for more. Armed with this new understanding, scientists can look at history and the future in a whole new light. The 1960 Chilean eruption is now a textbook example of dynamic triggering. The sheer power of the M9.5 quake sent waves strong enough to agitate the magma of Puyehue Cordon Caule, causing it to erupt less than 2 days later. Nowhere is this connection more obvious than the Pacific Ring of Fire. This massive arc around the Pacific Ocean is home to 90% of the world's earthquakes and 75% of its active volcanoes. It's a zone where tectonic plates are constantly colliding and diving beneath one another, a process that both builds the stress for huge earthquakes and melts the rock to feed volcanoes. It's the planet's perfect storm for these trigger events. Russia's Kamchatka Peninsula, a part of this ring, is a perfect natural lab. A megathrust earthquake there in 1952 was followed by increased activity at several volcanoes, showing how one big shake can have widespread effects, though scientists still debate the direct links for that specific event. This knowledge also helps us bust some geological myths. For years, people pointed to the 1991 eruption of Mount Pinatubo in the Philippines. It was the second largest eruption of the 20th century, and it was preceded a year earlier by a powerful 7.7 magnitude earthquake about 100 kilometers away. It seemed like a clear-cut case, but careful study showed the eruption was most likely its own boss. The volcano had started showing signs of unrest and rising magma months after the quake, and most scientists no longer see a direct causal link. Pinatubo serves as a crucial reminder. Not every earthquake near a volcano is a trigger. The volcano has to be primed and ready to go on its own. So, do earthquakes cause volcanoes to erupt? The answer is a resounding sometimes. An earthquake can't just create an eruption from scratch. It can't fill an empty magma chamber or build pressure that isn't there. Think of the earthquake as the final push. It's the nudge for a volcano that's already teetering on the edge, a system that's already loaded, pressurized, and ready to blow. Whether it's through the violent shaking of dynamic waves, the subtle stretching of the crust, or a disruption of its plumbing, an earthquake can provide that final, fatal disturbance. This knowledge is changing how we assess risk. Now, when a major earthquake rumbles, scientists don't just look at the damaged buildings. They immediately turn their eyes to the silent mountains, modeling the stress changes and listening for the faintest tremors that might signal a giant is waking up. The ground beneath us isn't a solid, static stage. It's a living, breathing system of almost unimaginable power. The secret connection between the shudder of a quake and the roar of a volcano is a chilling reminder that these forces are deeply intertwined, part of a single, dynamic, and sometimes very violent planet. We're only just beginning to understand the secret conversations happening deep within the Earth.